Stanford University.
All right. Well, a mathematical interlude we're going to begin with. The mathematical interlude is again about linear algebra, about vector spaces, but about the idea of operators. But before we do, before we get to operators, I want to say a few more things about vectors, a few more bits about the mathematics of vectors. Most of these bits have to do not so much with deep mathematics as with good notation. Good notation is worth an awful lot when you can just manipulate symbols in ways that are sort of prearranged and do it easily and comfortably. There's an enormous benefit in that for doing abstract mathematics, certainly, but also the abstractions, the mathematical abstractions of physics. The abstractions that we're going to talk about were largely due to Dirac, Paul Dirac, who really was the one who saw into the way that quantum mechanics really fits together. So let's talk about that. We have a space of states. The space of states, which we'll come back to, is, as I said, a linear vector space, meaning to say that you can multiply states by numbers to get new states, and these are abstract vectors. Abstract vectors. Maybe I throw too much in when I say the space of states. Just abstract vectors. You can multiply them by numbers, in our case complex numbers, and you can add them. And there are two kinds of vectors. There are the bra vectors and the ket vectors. They're roughly speaking related by complex conjugation. And a vector space has a dimensionality. The dimensionality is the maximum number of orthogonal vectors that you can find in that space. And once you know what the dimension of the space is, you can look for a basis of vectors. The basis of vectors is a mutually orthogonal collection of normalized, get the terminology down, orthonormal basis. Ortho means that they're all orthogonal to each other. Normal, the word normal means normalized, and normalized simply means that the vectors are of unit length. A collection of them that is maximal, in other words, that you can't find any more because there are no more directions left, that defines a basis, and the number of them is equal to the dimensionality of the space. Given such a basis, you can write any vector in the space as some kind of sum over those basis vectors. So we can write for any vector A that it's equal to sum over I. I here stands for the basis vectors. Oh, of course, a basis is not a unique thing. Just as there are many sets of mutually orthogonal vectors in three-dimensional space, there are many sets of mutually orthogonal vectors in an abstract vector space, but we pick one. We pick a set. Having picked that set and we label it I, we can write any vector as a sum alpha sub I, exactly those alphas which were referred to a moment ago. Alpha sub I, a set of complex numbers, a set of complex coefficients, times the ith basis vector. The ith basis vector I'm labeling I. This is a ket representation, but now what we can do with this is we can take the inner product with it. I want to try to calculate these alpha sub i's in terms of some quantities involving the vectors themselves. All right, so what we do is we take the inner product of both sides of the equation with the basis vector j, the ket vector j. On the left-hand side, we get the inner product of the vector A, which is the thing we're trying to express, and that's equal to the sum over I, alpha sub I, times the inner product of the vector j with the vector I. But the inner product of the vector j with this vector I is either 1 or 0. It's 1 if I and j are the same vector, and it's 0 otherwise. Why? Because they're orthogonal if I is not equal to j, and they're normalized, namely of unit length, if I does equal j. So this bracket over here, this product of bras and kets, is just the Kronecker symbol delta ji, 0 or 1, And when you do the sum, it just picks out one and only one contribution, the contribution in which I is equal to j. So on the right-hand side, you just get alpha j. No sum. The sum is collapsed to one term, and that's now equal to ja. All right, so what have we learned? We've learned that the coefficient here in the expansion of any vector is just the inner product of the jth vector with the target vector, with the vector we're trying to describe. The fact that I wrote a j there is irrelevant. It could also be alpha I. It doesn't matter which I or which j. The ith coefficient is an inner product. Now, I can use that to rewrite the sum up here. I now know what the alpha sub i's are. They're these guys over here. So let's rewrite this. Sum over I. I'm going to start with alpha I. With I. And then write alpha sub I. I'm going to write alpha sub I next to it over here in the opposite order. That's allowed. Nothing non-commutative at this stage. Now I want to write alpha sub I. So I write I A. That's a basic formula that any vector can be rewritten in terms of its coefficients, or in terms of its inner product with the basis vectors times the basis vectors themselves, summed over I. It's kind of a pretty formula, and it comes back over and over again. What it says is whenever you see this summation of I times I in that form, you can sort of throw it away. It's just A equals A. But it's an expression for a vector in terms of its components. All right, so that's one simple fact. The same thing is true for bra vectors. Exactly the same thing is true for bra vectors, and you would write it in the following form. A bra vector is also a sum over I of the inner product of the bra vector with the basis vectors times the basis bra vectors. The basis bra vectors are just the complex conjugates, if you like, of the basis ket vectors. Both of these equations are true, and we're going to find out that they're enormously useful. They're enormously useful and powerful, even though they were very, very simple. All right, now we come to the notion of linear operators. States in quantum mechanics are vectors, and we saw a little bit about how that works in the case of a single spin. Observables. Observables mean the things that we measure. The things that we measure, the objects that we measure, the quantities that we measure. The observables are related to linear operators in the space. All right, so what is a linear operator? And it'll take us the rest of the evening to understand in any detail what it has to do with observables. So put that out of your head for the moment. We're just doing a mathematical interlude now. What is the notion of a linear operator? A linear operator is a process, if you like, which you apply to vectors. Somebody or other, I can't remember who, it might have been John Wheeler, liked to describe these things as machines. He would say a linear operator is a machine with two little ports in it. Into one port you put an input vector, and then you turn the wheel and out comes an output vector. So it's a thing which acts on an input vector to give an output vector. So let's call M a linear operator. Linear we'll come to. So far we're just talking about operator, a machine. In goes one end, out comes another end, and we'll talk about what it means for it to be linear in a minute. All right, so M is some operator, and that means that given any vector, When m acts on it, it simply gives another vector. Unique. Given any a, it gives a unique b. That does not mean, the converse may not be, converse, opposite, I don't know, may not be true. It may not be that given a b on this side, that there's only one unique a that gives rise to that b, but it is true that m applied to any vector a gives a unique reflection of a, which is the process m acting on a. Now, what does it mean for m to be a linear operator? Well, first of all, m can act on z times a, where z times a is a vector. In fact, let's write that, yeah. M can act on z times a. Z times a is itself a vector because you're allowed to multiply vectors by complex numbers. Z is a complex number. The rule about linear operators is if they apply on constants times vector, they just give back the constant times what they would have given on a. All right, so it just means that a z, a complex number can be brought through m. M acting on twice a gives twice what m would have given on a. M acting on 3 times a gives 3 times what m gives on a. M acting on I times a, the complex number of I, just gives I times whatever m would give on a. That's the first rule about linearity. And the second rule about linearity is that if m acts on the sum of two vectors, a plus b, then what you get is just a sum of what the machine spit out for a and what the machine spit out for b. What the machine spits out when you put in a plus b is just a sum of what comes out, m times a plus m times b. And that's it. That's the notion of a linear operator. There's no more to it than that. Or at least that's the full set of rules about linear operators. Now let's see if we can be more concrete about them. And see if we can learn to manipulate with them. Let's suppose that m times a equals b. Here I've used b as a piece of the input, but now b is the output. A and b are just letters. I can use them any way I want. M times a equals b. I'm interested in the component of b along the axis I. By that I mean these objects over here, the alphas, they are the components of the vector a along the various basis vector directions. So alpha sub i's are the components of the vectors, and I'm interested in the components of the output vector. I would like to know in a concrete way what are the components of b. So to find out, I just project them onto the direction I. A, M, I. All I've done is in both sides of the equation project, or to project this, to take the inner product with the vector I. This, by definition, is beta I. In other words, if I were to expand b in the same way I expanded a, I would use the coefficients beta I. That's what we learned up on the top board. This is beta I. How about over here? What can I do with this to rewrite things in terms of components? I want to rewrite everything in terms of components so they actually become arithmetical operations that you can do. Well, here's where we use this trick. That whenever you see a vector A, you can substitute for it a sum. Let's do that right in here. Where A is, let's substitute I. I haven't substituted yet. Now, The summation variable is not I in this case. I've used as the external non-summation variable here. So let's sum over j. Doesn't matter what we call a summation variable. J A. I've stuck in for A the sum of the components times the jth vector, times the jth basis vector. But now, A times j, go up to the top again, that's just alpha j. So we now have a formula completely in terms of components. This is I, M, j. I'll get to this in a minute, but it's a number. Inner products are numbers. M times j is a vector, and you can take its inner product with I. All right? M times j is a vector, and vectors, ket vectors, have inner products with basis vectors, times j a, or times alpha j, that's equal to beta I. So all we have to do is give this object a name. What is this object? Just I'll tell you again. You have some operator, it's an abstract entity. You have a collection of basis vectors. You apply the abstract operator to the vector j and take its inner product with I and call the thing mij. It's a number. It may be a complex number, but it's a number. In other words, it's possible to characterize linear operators by what are called their matrix elements. These are called the matrix elements of the linear operator M. This times alpha j summed over j. I left out the sum over j here. Let's put it back in. Sum on j is equal to beta I. If somebody hands you the collection of mij's, and somebody hands you a vector in the form of its components, you can then start sweeping through it and calculating what the components of the output are in terms of the input. Mij is a matrix. It has two indices. It's a square matrix. If the dimensionality of the space is n, then M is an n by n matrix, a square matrix. It's a square matrix. Alpha can be regarded as a column. Alpha can be regarded as a column, and the output is also a column. It's a column because A was a ket vector and B was a ket vector. All right, so another way to write the same thing, this is one way to write M times A equals B. Well, here's one way to write it, abstract. Here's another way to write it as a concrete sum. And the third way is to recognize that this is just the multiplication of a matrix times a column vector. You write the matrix M by displaying all of its components, M11, M12, M13, dot, 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 M21, M22, dot, 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 dot. It's just an array that exhibits the matrix elements. We'll now learn to call these the matrix elements of M times the column vector A, alpha 1, alpha 2, dot, 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 alpha n. And what is the rule? This, of course, is supposed to result in an output which is beta 1, beta 2, dot, dot, beta n. All right, what's the rule that's implied by this equation over here? It's very simple. If you want the first entry over here, you take the first row and you take its inner product with the column here. Not the inner, well, you can call it the inner product. M11 alpha 1 plus M12 alpha 2 plus M13 alpha 3, right down to the bottom. That's exactly this formula. M11 alpha 1 plus M12 alpha 2 and so forth is exactly the standard rule for multiplying a matrix by a column vector. All right, so now we have a third way to represent the action of a matrix on a vector. This is less abstract. It's concrete. If you know the matrix elements, you know exactly what to do with them. The only thing about it is it does depend on a particular choice of your basis vectors. The specifics of the matrix elements here and the column vector will depend on your choice of, once you pick a basis, you stick with it. But you could have chosen a different basis, in which case these components would have been different. The matrix elements would have been different. After all, the matrix elements are themselves related to the basis vectors. And so you lose something and you gain something by going to a matrix type representation. What you lose is the geometric idea of a relationship between two vectors that's independent of the basis choice. What you gain is a computational, actual mechanical algorithm for producing, or for the machine itself. Here is the machine. The machine is a matrix, and what it does is it grinds through M11, alpha 1, blah, 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 blah. Then it goes to the next row, does the thing again, goes to the next row, does the thing again, and just spits out the final answer. These things, of course, also true for ordinary vectors in three-dimensional space. They're not specific. We tend not to use them as much in three-dimensional ordinary vectors, but they're quite essential in quantum mechanics. Yes, Martha?
This may be getting ahead. Could the choice of basis vectors ever make a difference to whether or not you can see the solution to a problem?
Well, all right, the precise way you ask it, whether it can make a difference to the way you see through a problem, certainly a wrong choice of basis can leave you completely confused. I think what you really meant is can different choices of bases lead to different physical answers, and that had better not be. Then you're doing something wrong. Yeah, it's often the case that a convenient choice of basis will make your computations especially simple. And a bad choice of basis might make them horribly complicated. That's true, but at the end of the day, the answers should not depend on it, the result of an experiment. Okay, so now we have the idea of a linear operator operating on and several different versions of it.
Question?
Yeah.
Is it legitimate? It seems that within a definition of linear operator, you have an operator that gives you a ket vector from a bra vector or vice versa.
No. Linear operators act on ket vectors to give ket vectors.
Complex conjugation is not allowed.
That's right. Complex very good. All right. Well, let's the simplest kind of linear operator is just multiplication by a complex number. I just multiply a by a complex number and get another vector. It's basically the same vector, but twice as long or something. That is a linear operator. You might ask whether complex conjugation is a linear operator. I take the components of a vector and replace them by their complex conjugates. The answer is no, it is not. And you can check the definitions. Multiplying the components of a vector, or not multiplying them, but complex conjugating them is not. What it does do is it takes a vector, it's a different kind of machine, complex conjugation. It's a machine which takes a bra vector to a ket vector, or a ket vector to a bra vector. And that's strictly, it's called an antilinear operator. It's not antilinear. I mean, it's not the opposite of linear. It's just a word. Well, the reason it's a word, the reason it was called an antilinear is because the process of complex conjugation is in some deep way related to antiparticles, but we're not there yet. Yeah. All right, now let's talk about bra vectors. So far, we have defined our linear operators to act only on ket vectors. But every linear operator can also be given a definition. We need a definition, of course. We haven't defined it yet. We need a definition. But there is also a definition of any given linear operator acting on a bra vector. Okay, let's see if we can concoct a definition, and then we'll stick with that definition. What might be the rules for the action of that same linear operator when it acts on a bra vector? First of all, the standard notation, and it's very, very good to keep track of notation and to use the same notation over. It's not only neat, but it keeps things in order. When you act on a bra vector, put the corresponding operator on the right side of it. All right? It gives something. Take that something and take its inner product. Let's put a bracket around it to indicate that M acting on A is itself an entity. And now let's take its inner product with another vector, B. Well, if I removed the bracket here, I would have a symbol which would look like this, A, M, B. And I really wouldn't know if what I'm supposed to do is act with M on B and then take the inner product with A, or act with M on A and then take the inner product with B. The answer is, with the standard definition of how linear operators act to the left on bra vectors, it doesn't matter. In other words, we define the action of an M on an A to the left such that, and I'll show you that we can always do this, such that it doesn't matter which way we do it. Okay. A, M, B is the same as A, M, B, that you can remove the brackets. Okay, let's see that we can do this. In order to see it, let's start with the definition this way. Let's start with the definition this way. Where's my, okay. Start with the definition this way. And now I'm going to use that trick up on the top, where you write a vector by inserting, there's a name for this operation here. It's called inserting a complete set of states. Complete simply means it's a basis. It's called inserting a complete set of states. It did nothing. It took A and it rewrote A, but it rewrote A in terms of its components. So let's do that over on B over here. We can do the same thing over here. We can write that this is equal to B, J, J, summed over J. I'm not going to write the summation signs. Maybe I'll put them at the end out here. Summation I and J. All right, so this is the same vector as B. Then put M there. Let's put the bracket around it. Put M there. And now do exactly the same thing on the ket vector. Remember, the ket vector can also be expanded in the same way. So here we go. A, I. What do we see here? We see this is alpha star I. Why did I put the I? Why did I put the star there? Because the bra vectors are complex conjugates. So there's an alpha sub I. There's an Mij. I in a product of I, M times J, and then there is beta J. That's all we have here. This is summed on I and J. M with I on the left and J on the right, that's Mij, J beta, alpha I. And you can see from the way that we've written this that it doesn't matter if I first sum over J and think of M as acting on the ket vector beta, or I sum over I and think of M as first acting to the left on alpha. You get the same answer. It's just a double sum over I and j. You get the same answer. And so if you define, in other words, you can define m in such a way that it doesn't matter which order, or where you put the brackets. That eases your life. You don't have to remember whether you meant m acts on b and then you take the inner product with a, or m acts on a and then you take the inner product with b. Same thing. Okay, but that's the power of a nice notation. But now let's consider another question. Supposing that the linear operator m on a gives b. Incidentally, I'm using a and b all over the place in different ways. There it was just two vectors. Here, a is the input vector, b is the output vector. So let's suppose that the machine m, when you stick a into it, outspits b. We could ask, what's the corresponding bra vector relationship? Is there a linear operator which has the property that when it acts on, I'm not going to call it m yet. It's not m. Let's call it scripty m. Is there, for every m which acts on a to give b, is there a corresponding scripty m which acts on the corresponding bra vector b to give the corresponding bra vector over here? Well, yes, there is, and we're going to figure out how to figure out what it is soon enough, but it is not the original m. One example would be, what if m was just multiplication by a complex number? Then what would scripty m be? Multiplication by the complex conjugate number. So whatever m is, it's not necessarily the same as scripty m. It would be the same as scripty m if it was multiplication by a real number. But if it's multiplication by a complex number, then in general, it will not give the same relationship. We would normally just put a complex conjugate sign if we wanted to operate on the other direction. All right, the notation that is standard is to say that the operator which, when acting to the left, is the reflection, if you like, is the dual of the operator m acting to the right. That is not called m, it is called m dagger. The dagger is a operator version of complex conjugation. It's an operator version of complex conjugation, or a matrix version of complex conjugation. It's called Hermitian conjugation, but we'll get to these fancy words soon enough. Well, okay, this is abstract, but let's see if we can get to a concrete notion. Mij, the abstract operator, is equivalent to a concrete matrix. If I give you the concrete matrix, then I'm giving you m. The question is, in terms of that concrete matrix, is there a concrete matrix for m dagger? And the answer is yes. How do we find it? We find it just by proceeding dead ahead. I would like to know what the matrix elements, let's see which way I did it. Yeah. This is what I would call the ijth matrix element of m dagger. I don't know what m dagger is yet. I have a suspicion that's something to do with complex conjugates. But this is its matrix elements, concrete set of numbers. Can we find out what they are? All right. Yeah, I think I have to step back for a minute. Let me suppose that m acts on the basis vector to give I prime. I prime is just the result of sticking the basis vector into the machine, into the M machine, and this is what comes out. Let's suppose that's the result. Okay? Now let's take J M I. That's equal to J I prime. All I've done is take the inner product with J. Here's the matrix element of the matrix M, and it's just this inner product. That was a trivial operation. I didn't do anything. Okay? I didn't do anything very significant. If this is true, then by definition, M dagger acting to the left, what does M dagger acting to the left give on I? Okay, look at this equation here. M dagger, when it acts to the left, gives the bra vector B. All right, so that's all that dagger does, is it sort of turns the equation over. So what does M dagger acting on I give? It gives the bra vector I prime. If M dagger acts on the bra I, it must give the bra vector I prime. It just flips the equation from bras to kets. So what we have over here then is I prime J. That's the matrix element. That's this matrix element over here. Okay, so let's look what we have. We have the matrix element of M is the inner product of J with I prime. The matrix element of M dagger is the inner product of I prime with J. What's the relationship between these two?
Transposing complex conjugate.
Just a complex conjugate. If you take two vectors, A and B, and you think of them in the opposite order, the bra A times the ket B versus the bra B times the ket A, the relationship between them is just complex conjugation. So this here is just a complex conjugate of this. So what we've derived is that the matrix element, the ijth matrix element of M dagger, is the complex conjugate of the J-ith matrix element of M. So if I know the matrix elements of M, what do I do to get the matrix elements of M dagger? It's very simple. You complex conjugate, but that's not quite enough. You complex conjugate and you interchange I's and J's. You interchange I and J. Okay? Another way to write it is that M dagger Ij is equal to Mji star. So now we know a lot. We know how to construct operators which act to the left to do the same mapping that they did when they went to the right. They map the bra A to the bra B if the original operator did the same thing on the kets. All right, that's the notion of Hermitian conjugation. This is called Hermitian conjugation. The word Hermitian is named after some mathematician whose name was Hermite. And Hermitian conjugation is the process of interchanging I and J and taking its complex conjugate. In terms of matrices, if I have a matrix, this is an easy way to remember it, M11, M12, dot, 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 M21, M22. If that's the matrix representing M, then the matrix representing its conjugate, its Hermitian conjugate, is to simply interchange rows and columns That means reflecting it about the diagonal and then complex conjugating. Interchanging I and j, that's like interchanging M12 with M21. You just flip it about the diagonal and you complex conjugate it. So if I want the matrix elements of the Hermitian conjugate, well, I can't say it anymore, you just do what I said. You interchange rows and columns and you complex conjugate. Interchanging rows and columns is the same thing as reflecting about the diagonal. Right? You reflect about the diagonal, let's do it, and then you complex conjugate. Let me give an example. Supposing I have the matrix 2, 6 plus I times 7, 4 minus I, and 9. 9 plus I, okay, 9 plus I. What's the Hermitian conjugate of that? All right, you first flip it. Flipping it leaves the diagonal elements in place and interchanges the off-diagonal elements. So you flip it, 2, 9 plus I, 6 plus I times 7, 4 minus I. What is that process called of flipping it like that? Transpose. That's called the transpose. So flipping it is a transpose, but then you have to complex conjugate it. Complex conjugating just means wherever you see I, put minus I. So this becomes 4 plus I, 1 minus 7I, and 9 minus I. And that's the matrix that represents the Hermitian conjugate of the original matrix. So it's easy. It's easy, it's concrete, and it's also abstract. It has an abstract side. The Hermitian conjugate just allows you to turn an equation from a bra vector to a ket vector. And in terms of concrete matrix elements, you flip I and j, and you complex conjugate, and that defines M dagger. Now, as I said, in general, these matrices are thought of as complex objects. And the notion of complex conjugation is replaced by this Hermitian conjugation. Simultaneous flipping and, right. Now, what is a real number? A real number is one which is its own complex conjugate. If I write that z is equal to z star, you jump up and you say, that is a real number. There's a corresponding notion for operators. It's the notion of an operator which is its own Hermitian conjugate. An operator which is its own Hermitian conjugate, that means you interchange and complex conjugate and you get back to the same thing. That is called Hermitian. Hermitian is the analog for matrices, or the analog for operators, of real. All right, so what it says, a Hermitian matrix. Now let's specialize to the case of Hermitian matrices. And just spell out Hermitian for you. Hermitian for matrices is the analog of real for numbers. A Hermitian operator or matrix is one which is equal to its own Hermitian conjugate. In terms of matrices, it's Mij is equal to Mji star. Let's try to see if we can construct a Hermitian matrix. Let's see if we can construct a Hermitian matrix. The first thing about Hermitian matrices is their diagonal elements are always real. Take a diagonal element. For a diagonal element, I and j are equal. Ij is the same as ji if on the diagonal. So that says that for the diagonal elements, they're always real. So a Hermitian matrix, first of all, has real diagonal elements. 1, 7, I don't know, I like 7. Minus 2.6 on the diagonal. off the diagonal, they have the property that when you reflect them, they simply complex conjugate. So if we were to put I over here, we would put minus I over here for a Hermitian matrix. If you were to put 4 minus I over here, you would put 4 plus I over here. And if you had 5 over here, you'd put 5 over here. All right, so a Hermitian matrix has the property, first of all, the diagonal elements are real, and the off-diagonal elements, not symmetric, but a different kind of symmetry, a symmetry where when you reflect them, they complex conjugate. That's called a Hermitian matrix. A Hermitian matrix has an enormous importance in, Hermitian matrices have enormous importance in quantum mechanics. They represent the observable quantities, the measurable quantities, the things that you can measure. We're going to come to that, and we're going to do a bit of that, especially for the single spin, I hope tonight. But before we do, we have to know a little more about Hermitian matrices. In particular, we need a concept, the concept of eigenvector and eigenvalue. Right? Now, I know that I'm going fast, and I know I'm quite aware that if you don't know these ideas, you're going to have to struggle tonight to keep up, but they're standard ideas. There are lots of textbooks on linear algebra. You can find it, and you can sit down quietly and learn these ideas in about 2 hours, I would say. 2-3 hours. Okay, so let's talk about Hermitian. Well, let's first talk about eigenvectors and eigenvalues. We can even think about these things, incidentally, in ordinary three-dimensional space, where the vector space is just a space of ordinary 3 vectors. There are operators. They're represented by matrices, and those operators operate on vectors to give other vectors. And typically, if a matrix is at all interesting, or if an operator is at all interesting, whatever it means to be interesting, well, if it's at all a little bit complex, it will generally have the property that if you put a vector into the machine, the vector that comes out will be pointing in a different direction. That will be generally true, generically true. So directionality is not preserved by linear operators as a rule. On the other hand, there may be particular vectors, and typically there are particular vectors that when you apply a matrix, those vectors will depend on which matrix you're talking about, or an operator. There may be specific vectors associated with a specific operator that do simply get multiplied by numbers. In other words, they come out in the same direction. An example of a operation, a linear operation on a vector, is a rotation about an axis. That can be represented by a matrix. In 3 dimensions, if you rotate the vector space about some axis, then generally speaking, an arbitrary vector will wind up in a different direction. However, there is one particular direction for which that doesn't happen, namely along the axis of rotation. If you rotate about the axis of rotation, the vector comes out pointing in the same direction. It comes out a multiple of itself. Now, in this case, simply equal to itself. All right, so that's the notion of the eigenvectors of an operator. They are the vectors, if there are any. They're not necessarily any. For example, in rotations about 2 dimensions, there are no eigenvectors. There are no directions which come out unaffected. But so in general, there may or may not be eigenvectors. But if there are eigenvectors, they're defined in the following way. Again, I'm going to use M for the generic operator. M acts on an eigenvector. Let's call the eigenvector I. I for eigen. Now, of course, I is not for eigen. Eigen begins with an E. But I'm going to call it I anyway. All right? If M acts on one of its eigenvectors. Eigenvectors are not things which are independent of the matrices. Given a matrix or an operator, it has certain eigendirections or certain eigenvectors. And the rule is, or the definition, is the set of vectors which just get multiplied by numbers. Let's call for the ith eigenvector here. The eigenvalue is called lambda I, and it simply multiplies the input. Now, different eigenvectors of the same matrix will have different eigenvalues. There may be, and in general, that's the generic situation. If there are several eigenvectors, they will have different eigenvalues. However, the eigenvectors are not completely unambiguous. If you take an eigenvector and multiply it by a number, the result is still an eigenvector with the same eigenvalue. If I multiply this equation by a complex number z, I can bring the complex number z through, and I'll find out that any numerical, even complex numerical multiple of an eigenvector is also an eigenvector. So strictly speaking, you should talk about eigendirections. The set of vectors is including or not worrying about their length, so to speak. But in any case, this is the direction of this is the definition of an eigenvector. All right, some matrices have eigenvectors, other matrices don't have eigenvectors. There is something important about Hermitian matrices, or Hermitian operators. Hermitian operators not only have eigenvectors, they have a complete set of eigenvectors. Complete means that there are enough of them to expand any vector, and even better, they have an orthonormal family of eigenvectors. In general, the different eigenvectors will have different eigenvalues, as I said, but it will be true that if a matrix is Hermitian, it has, and the dimensionality of the space is n, there will be n mutually orthogonal eigenvectors. In other words, the eigenvectors of Hermitian matrices define a basis. I'm going to let you prove part of that theorem. It's a very easy theorem to prove, and I'm going to prove the other half of it. I'll prove the half that says that if you have two eigenvectors with different eigenvalues, and that's the generic situation, that the eigenvalues are all different. If you have two eigenvectors with different eigenvalues, we will prove that they're orthogonal to each other. Your job is to prove that you won't run out of eigenvectors until you have n of them. It's not hard. It's not hard. In any case, it's true. All right, so let's prove that if we have two eigenvectors, M is a Hermitian. All right, M is Hermitian. M equals a Hermitian matrix. I use matrix and operator synonymously, which means that M equals M dagger. Okay, let's suppose that M is Hermitian and it has an eigenvalue lambda I. The first observation is that the eigenvalues of Hermitian matrices are real. That even comes before what I said previously. If there is an eigenvalue, it is real. Okay, how do we prove that it's real? All right, let's prove that it's real. Well, let's take this equation and flip it over into a bra equation. To flip it over into a bra equation, I flip I take M and I replace it by M dagger. Well, that's not going to do much because M is equal to M dagger. And on the right-hand side, I flip I, and what do I do with lambda in general? Complex conjugate. Complex conjugate. Lambda I. So far, we haven't proved that it's real. Right. Every time you flip from bras to kets, you have to complex conjugate all the numbers that are there. All right, but now, assumption, M is Hermitian, so it's equal to its own Hermitian conjugate. And now we have this equation. Now let's take the inner product of both of these equations with I. In the upper equation, we're going to take the inner product on the left with I. And what does that give us? That gives us I times lambda I. Let's do the same thing over here, except now multiplying on the right. This and this are obviously the same. M with I on the left and I on the right is the same as this. But this is not obviously the same. Not unless lambda is equal to lambda star. I here is the same as I here. That cancels out. And therefore, we come to the conclusion that if a matrix is Hermitian, if it's equal to its own Hermitian conjugate, then its eigenvalues are equal to their own complex conjugates, and they are real. Eigenvalues of Hermitian matrices are real. That's the first step. Now let's prove that if we have two different eigenvalues, the corresponding eigenvectors must be orthogonal. Now remember what orthogonal means from a physical point of view. It means physically distinct, that there's an experiment that you can do to distinguish the two of them unambiguously. That's what orthogonality means from a physical point of view. Let's prove that the eigenvectors of M with different eigenvalue are orthogonal. Different eigenvalue, physically distinguishable. You should keep that in your head. Okay, so here we are. Let's start with M on I equals lambda I. And M on J equals lambda J. Two different eigenvectors, I and J. First thing we'll do is turn this one over and turn it into a ket equation. A bra, it is a ket equation. We'll take this one and turn it into a bra equation. So that looks like this. J, M dagger, but M dagger is the same as M, equals the real number lambda J, eigenvalues of Hermitian matrices are real, times J. Now, here we have, okay, so we have two equations. What can you do to them so that we can relate them? What we can do with them to relate them is to multiply this one by J on the left and this one by I on the right. And we will get the same expression on the left-hand side of the equation. So let's do that. J, I. What we have on the left is the same on the upper and lower equation. What we have on the right is not necessarily the same. So let's require that it's the same. Requiring that it's the same says that lambda I minus lambda J times the inner product of J with I must equal 0. I've just written that this is equal to this, and then transposed. All right, so lambda I minus lambda J times the inner product of Ji equals 0. Well, if the product of two things, and I have two things, lambda I minus lambda J and the inner product of Ji with J, if the product of two things is 0, it says unambiguously at least one of them is 0. It usually says one of them is 0, okay? The inner product of I and J may or may not be 0, but let's take the case where we know that the eigenvectors correspond to different values of the that the eigenvalues are different. That's what I'm interested in. I'm interested in eigenvectors corresponding to different values of the eigenvalue. So by assumption, lambda I is not equal to lambda J. the conclusion is that the inner product of I with j must be equal to 0. So what does that mean? That means that I and j are orthogonal. So we now have a theorem. The eigenvectors of Hermitian matrices with different eigenvalue are orthogonal. Let's just take the generic case where all of the eigenvalues are different. We can come back to what happens when some of them may be the same. That's not important right now. If all the eigenvalues happen to be different than each other, then all the eigenvectors are mutually orthogonal to each other. If there are enough of them, and your job is to prove there's enough of them, they form a basis. In other words, this collection of things called I and j here is a special case of the kind of basis which we labeled with small I and j, but it's the basis of eigenvectors. It's the basis of eigenvectors of the Hermitian operator. As I said, Hermitian operators will be identified with observable quantities, and to say that eigenvectors are orthogonal has something or other to do with physical differences that are measurable unambiguously between those states of the system. Okay, we are now prepared to state the principles of quantum mechanics. We have enough mathematical information or enough mathematical formalism to state the entire show. We can put on the blackboard now what quantum mechanics is and what it says, and what the rules are, or what the correspondences are, what the what the physical meaning of these various things are. You won't understand this the first time around. It'll be foreign. It'll be peculiar. What is he talking about? But of course, we'll work it out in examples, and we'll see how the ideas work. So don't get disturbed if what I throw at you now sounds a little bit meaningless. That's okay. By the time we're finished with some examples, it should be clear how we use this. All right, first of all, there are measurable quantities. The result of a measurement is always a real number. It takes at least two measurements and somehow two compatible measurements, two measurements that can both be performed simultaneously, to measure a complex number. Right? The basic ingredients and the basic measurables are real numbers. That's what comes out of your detector. You can measure two of them if you can measure two of them, if it's possible to simultaneously measure two things, and put them together into a complex number, but it really is just two measurements. So each measurement, each thing that you measure, has a real result associated with it. The physical measurables, they're called observables. In quantum mechanics, they're called observables, the things that you can measure. The observables are identified with Hermitian matrices, or Hermitian operators. Observables, whoops, not Q, where did I get Q from? I won't write equals, are represented by, we'll just put an arrow, are represented by Hermitian linear, of course, operators. First statement. Let's just think, in studying the spin in a rough and loose way, we sort of identified some observables. The observables that we identified were the components of the spin. The observables that we could identify were associated with our apparatus. Point your apparatus in some direction and measure the spin along those directions. We said, if we measured the spin along the z-axis, we called it sigma z. We can measure it. Or we could turn our apparatus on its side and measure sigma x. Or we can turn the apparatus from the x-axis to the y-axis and measure sigma y. We talked about those things. We didn't talk about sigmas being Hermitian operators. fact, we didn't talk about them being operators at all, but we did talk about measuring them. These will become Hermitian operators in time. Okay? All right, next, the possible values that a given observable can take on. What are they for sigma z? What are the possible +1 and -1, right? Okay? The possible observable values measured in an experiment, those observable values are the eigenvalues. They're real because the matrices are Hermitian. The eigenvectors, what about the eigenvectors? The eigenvectors correspond to states. States, vectors. States, vectors. The eigenvectors are the states in which the corresponding quantities are definite. In other words, in which the measurement of them is unambiguous. Oh, well, let's follow through on this here a little bit. For all three of these observables, the eigenvalues had better be +or -1. Okay, now let's come to the eigenvectors. The eigenvectors, for example, the eigenvector with a given eigenvalue is a state of the system where if you measure that particular observable, you will definitely get the eigenvalue associated with that eigenvector. So the eigenvectors those are, I think I have it backwards. We should put eigenvectors on this side. And on the left side, the physical meaning of them. The physical meaning is states in which observable has unambiguous result. Example, we talked, for example, about the states up and down. Those are states in which sigma z had definite values. When you're up, sigma z is definitely 1. When you're down, sigma z is definitely -1. Any other vector, sigma z is statistically either + or -1, but with a randomness. Okay. So, up and down must be the eigenvectors of sigma z. Left and right were the states in which sigma x was unambiguously either +1 or -1. So left and right must be the eigenvectors of sigma x, whatever sigma x is. We're going to try to figure out what sigma x is knowing its eigenvalues, knowing its eigenvalues and its eigenvectors. And what was the other two called? In and out, I think. Yeah. In and out were the eigenvectors of sigma y. So we have 3 connections, and now a 4th connection. Given a general state, not an eigenvector, given a general state A, somebody made an electron or a system of some sort and left it in the state A, then we can talk about what is the probability that we measure the eigenvalues of M at different values. There may be several different eigenvalues. In this case, they would be +1 and -1, but more generally, 1,000 eigenvalues, 1,000,000 eigenvalues, whatever the number is, labeled by the label I. What is the probability that when you measure M, you get lambda I? That's the last piece of thing here. So on the left-hand side, we put probability, physical meaning, probability, and I'll write it just as the probability to measure I. No, to measure lambda I. I'm sorry, to measure lambda I, that the result of the experiment comes out a particular eigenvalue of the observable m, whatever m is. That is related, not related to, it's essentially equal to, well, the two pieces, comes in two steps. First, you calculate, if you have the vector A, the vector which you start, that's the state of the system, you take its inner product with the eigenvector I. The projection of A onto I, the component of A in the I direction. Now that in general is a complex number. That is not the probability. You multiply it by its own complex conjugate to get a real positive number, and that is the probability. We can multiply this by its complex conjugate, or we can just write it IA. This IA and AI are complex conjugates of each other. We can also write this as the absolute value of IA squared. The individual components, before we square them, are called amplitudes. They're called probability amplitudes. Probability amplitudes are things which you multiply by their complex conjugates to find probabilities. They're real, they're positive, and that's the fourth postulate of quantum mechanics. Now, they're not all independent. I use them because they're reasonably intuitive. In fact, you can probably get rid of at least two of them and prove them from the others, but we don't need to do that. This is a good starting point. And these are the basic four postulates of quantum mechanics. Okay? The other postulate is that when you measure a quantity, you prepare the system in a state of definite value of that quantity. I won't bother writing that down. When you measure something, you are, in effect, pushing it into a state of definite value of that quantity, depending on what the outcome of your experiment is. If your outcome measures some particular, if the outcome of an experiment is some particular eigenvalue, that means you've pushed the system into the state, into the eigenstate of that quantity with that eigenvalue. I won't write that down. It takes too many words to write it down.
It's under the P, the probability.
Do it again.
I
Sit in.
Yeah. Then next to the P, what is that? I can't read your handwriting.
P-R-O-B.
Oh, prob. P-R-O-B. Prob. It's probably probable. Probably probability. Yeah. This reads the probability of measuring lambda, oh, it is lambda I. Lambda I. The probability of measuring lambda I is the square of the inner product of A with I. It's, if you like, it's the projection of A onto the ith direction, or the component of A in the I direction. Now, there's an implication here. There's an implication here about the nature of state vectors coming from the assumption that total probabilities are equal to 1.
To be normalized.
What's that?
It just said they have to be normalized.
Yeah, yeah. Let's work that out. If you want the total probability to add up to 1, then you want the sums of all these objects, when you sum over I, over the various possible values of that you can measure, you want that to equal 1. So you want the sum over I for any allowable state A. We want the sum of A, I, A to equal 1. Now, I is a basis. And if you go up to the top equation there, you have equations which tell you how to deal with exactly this combination What is the sum over I of I, A? It's just A. So what this says is that the inner product of A with itself should equal 1. The total length of A should be equal to 1. That's not too surprising that that's what this says. This says the sums of the squares of the components of A add up to 1. For ordinary vectors, that would just say the length of the vector was 1, and that's what this says. The length of A is equal to 1. It's equivalent in terms of the alphas. We got rid of, yeah, the alphas are up there also. It's equivalent to the sum of alpha star I alpha I equals 1. Well, I, capital I. And so there is one combination of the alphas. This is one real equation. It's not a complex equation. It's a real equation. And that means there's one real combination of the alphas which has to be constrained. Alphas are not completely free, or the alphas are not completely free. Roughly speaking, the sums of their squares, or the sums of them times their complex conjugate, has to add up to 1. So that means there's fewer independent quantities than you thought. There is another fact which we have not gotten to yet. We will get to it. You can sort of see it from here. All probabilities, any probability that you ever may want to measure or that you ever may want to calculate or compare with experiment is always connected with a real quantity like this. The collection of such real quantities is invariant under a certain operation. The operation is multiplying the state vector by a phase. Everybody know what it means to multiply a thing by a phase? You multiply it by an e to the I theta. If you multiply all the components of A by the same overall phase, then every probability is unchanged. Every probability is unchanged. Even if you rotate bases, it's unchanged. So physical quantities don't respond to a change of the phase. That means there are 2 fewer degrees of freedom, 2 fewer parameters in the specification of a state than the collection of complex numbers that would define a vector in the abstract space. 2. One is the phase, the overall phase, and the other is the magnitude of it. We'll come back to that. Okay, that's taken us a long way. You're probably saturated, but I'm not, so we're going to continue. I'm on a high.
Questions?
Probability also has to be, can't be negative. It has to be.
Yeah, that's right. So these are always positive. Okay. Thing times its complex conjugate is always positive.
Is the evolution postulate
Is the what? Is the what?
The evolution postulate.
We haven't, yeah, we haven't gotten to that yet. How things change with time, yeah. No, we're at the level now of where we were in classical physics when we just said the state of a system is just a point among a set of things. That's about where we are. That's how far we've gotten. We've not talked about how things change. In particular, how the states of systems change. And we will come to that.
So back at the beginning when we had this example of measuring these qubits, and you had
We're coming back
the
to
apparatus at an angle, and you got the cosine of theta, right? So
we're going to do it. Okay, well.
Okay, I guess my question was that we somehow got the idea that cosine of theta is going to be the average of your measurements. Should it be cosine squared? No?
I see where you're going, but
Okay.
not mine. We're going to do it.
Can you say that last postulate one more time so I can get
Which
all that?
postulate?
When you measure something, you push it into the state you are measuring.
No. When you measure something, you get a result. The result is statistically determined meaning to say that you may get one result, you may get another result, but once you get that result, then you know what state the system is in. It's in the eigenstate of the quantity that you measured with the eigenvalue that came up on your, on your detector. Remember, when we had our apparatus and we measured sigma z, we said that not only measures sigma z, but it prepares the system in a state of definite sigma z. It leaves it over in a state in which sigma z is definite for the next measurement. That means it leaves it in an eigenstate of sigma z. Okay. Let's see if we can apply this to, to the spin system. You get a very general formulation, and now we want to try it out and see how it works. All right. So I want to start with the three observables, sigma x, sigma y, and sigma z, and see what I can learn about them. First of all, sigma z. Now let's start in the basis associated with the measurement of the spin along the z-axis. Let's take that as the appropriate basis. Sigma z has two eigenvectors. From the experiments that we talked about, we would have learned, had we done the experiment, that sigma z has two eigenvalues and two eigenvectors. The two eigenvectors we've called up and down, and they're associated with sigma z equals +1 and -1. Those must be the eigenvectors of sigma z and eigenvalues, and so we can immediately say sigma z times up is equal to up, +1 times up. Why? Because the measured value when we measure sigma z is going to be +1, that's the eigenvalue, and up is the eigenvector because in the up state sigma z is definite. What about sigma z on the down state? What should I write there? Is sigma z definite in the down state? Yes, it's always -1. It's going to be -1, and that means the eigenvalue is -1 times down. It's not sigma z times down equals up. That wouldn't be an eigenvector. An eigenvector has the property that when the operator acts on it, it gives the same direction back times the eigenvalue. So here is what we know about sigma z. Okay. Let's see if we can compute its matrix elements and exhibit it as a matrix. But when I say exhibit it as a matrix, I must pick a basis. I'm going to pick the basis up and down. First of all, one thing, up and down are orthogonal to each other. They must be, according to these principles, because if sigma z is an observable, it corresponds to a Hermitian matrix. If there are two different eigenvalues, the eigenvectors must be orthogonal for a Hermitian matrix. And so up and down, well, we first of all learn that up and down are orthogonal. That's one fact. So it doesn't matter whether we write up, down, or down, up. I mean, we could write it in the opposite order. Let's see if we can compute the matrix elements. The matrix elements are just the array that we get when we consider the four possibilities. They're going to be 2 by 2 matrices. And the four possibilities are going to be, first of all, we take the inner product of this back with up. That'll be the up-up matrix element, or the 1-1 matrix element. What is that going to be? I'm not sure I want let's do it over here. Let's calculate up, sigma z up. That's equal. Sigma z acts to the right to give us up, +1, well, +1 is just 1, times up. Just the inner product of up with itself. And since up is a basis vector, it's normalized and this is just equal to 1. Its magnitude is equal to 1. I can choose it to be equal to 1. It's positive. Yeah, it's positive, it's real, and it's just plain 1. So up here in the up, up, or the 1, 1 place, it's just 1. Now, what about the off-diagonal element? The off-diagonal element, that's an off-diagonal element there. That's going to be equal to the inner product of down with up. What's that? All right, 0 over here. I would get exactly the same thing if I put down over here and up over here. Then I would use this equation over here. Let sigma z act on down, and then take its overlap with up, and I would get 0 again. And the last one is down sigma z down. What is that? Well, you go over to here. Sigma z times down is minus down. So this is just equal to minus down, down. And what's that? Minus 1. So this is the matrix that's associated with sigma z. When it acts on a vector, on a column vector, in particular when it acts, what is the column vector that's associated with up? It's just a 1 in the top and a 0 in the bottom. All right, so let's just try this. 1, 0. What do we get? We get 1 times 1 is 1. 0 times 0, 0. We just get the same vector back. That's good. Okay. Same thing. We'll get. It's guaranteed that we'll get the right, that the eigenvectors are what they're supposed to be, namely just up and down, and that the eigenvalues are +1 and -1 in the right way. All right, so we found one of the sigma matrices, sigma z. These are, of course, well, not of course, they're called the Pauli matrices, sigma x, sigma y, and sigma z. Let's see what we can find out about sigma x. Now, if I use the x basis, if I use the basis of left and right, of course I would just find exactly the same thing. But I want to stick with the up-down basis. I want to stick with the up-down basis, but find out what the matrix elements of sigma x are. Now, what is the property of sigma x? The property of sigma x is that its eigenvectors are left and right. So, for example, sigma x on right, that equals right. And what about sigma x on left? Equals minus left. Those are the two possible values that sigma x can take on. Left and right are the eigenvectors, in other words, the states in which sigma x has definite values, +1 and -1. And this is what I know about sigma x. But I want to find its matrix elements in the up-down basis. So what I really want then, let's come over to here and see if we can compute in the same basis. What did I do with the Pauli matrix? Did I erase it? I worked so hard to get it. Sigma z is equal to 1 minus 1, 0, 0. Now we want to try to get sigma x. So the first step is erase the blackboard. And let's start one by one. There are 4 matrix elements. Let's do them one by one. Up, sigma x, up. Now what we have to know is that up is equal to left plus right over the square root of 2. You remember that? We originally defined left and right to be up plus or minus down over the square root of 2, but then we can solve for up and down in terms of left and right. Down is left, it's right minus left. With the notation we had last time, it was it's right minus left over root 2. So all we have to do is plug them in. On the left here, we have left. You know, I'm gonna abuse notation and just write this as left plus right over square root of 2. This is a meaningless symbol, but I think you know what I mean. I mean the bra vector left plus the bra vector right over the square root of 2, but too many vertical strokes and I get confused. So let's just write it as left plus right over the square root of 2, sigma x left plus right over square root of 2. First of all, I can take out, this is the, what is this thing? This is sigma x up, up. There it is. It's the up, up entry, one that goes up in here. All right, first of all, there's a factor of 2 that I can take out, square root of 2 from here and a square root of 2 from here. That's altogether 1/2. And now let's look at this. What happens when sigma x hits left? It gives back left except with a minus sign. Right? What happens when sigma x hits right? It gives back right with a plus sign. So when sigma x acts on this, what it winds up giving, you can take the sigma x away and just remember what it does. It gives right minus left instead of right plus left. It hits the vector right and gives +1. It hits the vector left and gives -1. Again, these are not things to be numerically added. These are vectors, the right vector minus the left vector. And now all we have to do is take the inner products. Well, the inner product of right with right is what? 1. The inner product of right with left is 0. The inner product of left with right is 0. And the inner product with left -1 when you account for this minus. The result is they cancel. All right? 1 minus 1. Or equivalently, the inner product of, well, okay, 0. So first of all, there's a 0 over here. That's the up-up matrix element. It's easy to get the down-down matrix element. The down-down matrix element, you would do exactly the same thing, except that you would start with right minus left, right minus left, right minus left, sigma x. And then you would say that when sigma x hits right, it's plus right. When it hits left, it gives minus left. So when sigma x acts, it takes right minus left to right plus left. And what's the inner product of right plus left with right minus left? 0 again. Right with right is 1, left with left is -1, and the cross terms are just 0. So there's a 0 over here. Now, looks like all we're going to get is zeros, but that can't be right. So let's try up, down. All right, we try up, down. Let's put up, down there. Up will be right plus left. We'll have sigma x. And then down is right minus left. What happens when sigma x hits right plus left? It makes right minus left. And now what's the inner product? The inner product of right with right is 1. The inner product of minus left with minus left is also +1. So they add. And again, the cross terms between right and left are 0. So we get 2 divided by 2, which is 1. We get a 1 up here. And if we work it out, we'll get another 1 over here. All right, so now we've got sigma y. Let's just stop for a minute and say, what is it that we have? We have a pair of linear operators, or a pair of matrices, whose eigenvectors are, this fellow's eigenvectors here are up and down. This fellow's eigenvectors are right and left. They're exactly what we were talking about on the previous blackboard. the states in which the observables have unambiguous results are the eigenvectors. That's where we are. Now, the last one is sigma y. Okay. What do we know about sigma y? In and out are the eigenvectors.
The one we just did is sigma x, right?
The one we just did is sigma x.
You wrote sigma y then. You wrote sigma y.
Oh, sigma x, sorry. Actually, don't think I wrote sigma y. I think I just failed to cross the x. I think. I don't know, maybe I wrote sigma y. All right, the next one is sigma y. And here I'm going to leave some of the algebra. It's very easy to you, but let's see what the rules are. Oh, incidentally, no, I think we're okay. We know the rules. Okay, so there was in and out. I cannot remember which one was which, so I'm going to fake it. And if it comes out wrong, it comes out wrong. I think in was up plus, I think, I times down, and out was up minus I times down, and I think I left out factors of square root of 2. Incidentally, you can check that in and out are orthogonal to each other. Okay, there's in and out. Can we find a matrix which in and out are eigenvectors with eigenvalue +1 and -1? It's getting late. It's very easy. Leave it to you. I will simply tell you what that matrix is. It's unique. It's unique. If you know the eigenvectors and you know the eigenvalues, it's unique. One way of doing it is to solve for up and down in terms of in and out. Once you've solved for up and down in terms of in and out, and you know how the matrix acts on in and out, you're finished. The last one in the multiplet here, now I am writing sigma y. Similar to this one, but it's O minus I and I. All right, so a little exercise. You don't really need to go and prove this. You can do a different thing. You can take this matrix and show that these are the eigenvectors of it. You just show that these are the eigenvectors of it. You take this matrix and show that its eigenvectors, what does that mean? It means that its eigenvectors are 1i and 1 minus I. The square root of 2 doesn't matter. Eigenvectors are eigenvectors. They don't care about the square root of 2. Okay. These are the three Pauli matrices that represent the components of the spin in different directions. I think that's enough for tonight. What I was going to do, and I have in my notes, was exactly this question. What happens if you have a component of spin along an arbitrary direction? Can we show, using what we know, that the we'll do this next time. We'll do this next time. If we have a component of spin along an arbitrary direction, and we want to calculate, using the principles, we want to calculate what the probability is for the measurement of sigma z in various, either plus or minus. We should be able to do it. We have enough information. I think it's probably more than we can yet handle for tonight. I think we did a lot for tonight. Probably more than reasonable.
Am I wrong to say those u's need to be negative to make those two orthogonal? Does one of the u's need to be negative to make those?
No. No, you know what you're missing? You're missing that you have to complex conjugate. If you want the inner product of in with out, you multiply 1 times 1 and then add I, not times minus I, but I times plus I. Yeah. Yeah. The only way that somebody like me knows so quickly what you're thinking is having made the same mistake, of course. Sometime in the past. Okay. All right, we're finished for tonight, I think, unless there's questions.
For more, please visit us at stanford.edu.